So far, we've used the definition of a vector space to do some basic proofs about the zero vector and the negatives of vectors. Now, let's see some more examples of how algebra with vectors is just like normal algebra. A commonly used theorem in algebra is known as the zero factor theorem, which says that if the product of x and y is equal to 0, then either x equals 0 or y equals 0. This is true for scalar multiplication of a vector as well. Let's see why. Let's prove that if V is a vector space and x is some vector in V and a is a scalar, let's show that if ax equals the zero vector, then either a is 0 or x is the zero vector. Let's do a proof by contradiction. So first, let's assume that ax equals 0, the zero vector, and that a is not 0, and that x is not the zero vector. Then since a is not 0, I know that I can divide by a, so let's multiply both sides by 1 over a. Then using property 6 of the definition of vector spaces, I can write this as 1 over a times x, and that's equal to 1 over a times the zero vector. Now, this is clearly going to cancel out, and we've already proven that anything times the zero vector is the zero vector. So this simplifies to 1 times x equals the zero vector, and I know that 1 times x is just x by property 5. Okay, so we have now that x is equal to the zero vector, but we assumed up here that x is not the zero vector. This gives us a contradiction. So we assumed that it was false, and we've come to a contradiction. Therefore, if a times the vector x is equal to the zero vector, then either a is equal to 0 or x is the zero vector. In regular algebra, if I have ax equals bx, and I know that x is not equal to 0, then I can divide both sides by x, cancel the x's, and we have that a equals b. This doesn't work for vectors because there's no such thing as division by a vector x. However, the same property still holds. If a times a vector x is equal to b times the same vector, and it's not the zero vector, then we still have that a equals b. Let's see why. If x is a vector and a and b are scalars, and x is not the zero vector, let's show that if a times the vector x is equal to b times the vector x, then a equals b. So we have an if-then statement. We want to prove if ax equals bx, then a equals b. So we'll start by assuming ax is equal to bx. Now I know the additive inverse, the negative of bx exists, and I'll add it to both sides. So I have ax minus bx equal bx minus bx. Now, by the definition of the negative of a vector, by the definition of the additive inverse, I have that ax minus bx equals the zero vector. Now, using property 8 of the definition of a vector space, I can factor out the vector x. And now, using the theorem that we just proved, we have either a minus b is equal to 0 or x is equal to the zero vector. But we know that x is not equal to the zero vector, which means a minus b is equal to 0. So this means that a equals b. Therefore, we've shown that if a times x is equal to b times x, and using the assumption that x is not the zero vector, then a is equal to b. Similar to what we just proved, let's show that if ax equals ay and a is not equal to 0, then x equals y. Meaning that with vector algebra, I'm allowed to cancel scalars on either side of an equality. So if x and y are vectors, and a is a scalar, and it's not 0, let's show that if a times x equals a times y, then x equals y. So again, we have an if-then statement. Let's assume the if part. Then, since a is not equal to 0, I can multiply both sides by 1 over a. Now, using property 6 of the definition of a vector space on both sides, I have 1 over a times x equals 1 over a times y. Canceling out, we have 1x equals 1y. And using property 5 of the vector space definition, we see that x equals y. Therefore, if ax equals ay and a is not equal to 0, we know that x is equal to y. Now, let's put all of these together and do some algebra with vectors. So we want to simplify 3y plus 5x minus 2y plus 2 times x minus y. First, I have 3y plus 5x minus 2y plus 2x minus y. Then I use the fact that I can distribute the 2 over the x minus y, so I have 3y plus 5x minus 2y plus 2x minus 2y. Now I will use the fact that vector addition is associative, meaning that these parentheses don't matter. Now using the fact that addition is commutative, so the order that the terms appear in doesn't matter, I will move all of the x terms to the front, followed by all of the y terms. From the first two terms, I can factor out the x, so I have 5 plus 2 times x. And from the three last terms, I can factor out the y. In the end, this gives me 7x minus y. Moving on to the next one, solve for w. If 5x minus w equals 2 times w plus 2x, let's solve for w in terms of x. So first I will distribute the 2 over the w plus 2x. Now I can add w to both sides. So I have 5x is 2w plus 4x. And I can add the negative of 4x to both sides. Simplifying these terms, I can factor out the x, and I have 5 minus 4 times x equals 2w plus 1w plus 4x minus 4x. So here this simplifies to 1x. This is equal to 2 plus 1w plus the 0 vector. These cancel out. Finally, I can use the fact that 1 times x is equal to x, and that this simplifies to 3w, and that anything plus the 0 vector is again itself. So we found that x is equal to 3w. Thanks for watching. Be sure to drop a like and subscribe to see more linear algebra and matrix stuff.